Good morning, class. Here's statistics practice test number 4, covering chapters 8 and 9. Chapter 9, inferences from two samples. Again, reminding you of the pledge that we have to be careful, making sure we do the work on our own. You can use formula sheet, tables, and a graphing calculator. In short, chapter 9 is the continuation of chapter 8, dealing with two groups. Here's an example. Among 843 smoking employees of hospitals with their smoking ban, 56 quit. Smoking 1 year later after the ban. Among 703 smoking employees from workplaces without their smoking ban, 27 quit smoking a year after the ban. Is there a significant difference between the two proportions? Use 0.01 significance level. As always, we are dealing with an application word problem. We have to write the given first and foremost. We are dealing with binomial distribution because there are two outcomes. Either the smoker quits or does not. So, and we are dealing with two groups. The first group, N and X, N is 843, X is 56. So instead of calling it N and X, we're going to call N1 and X1. For the second group, we're going to call it N sub 2, 703, X sub 2, 27, and of course, alpha is 0.01. So that's the first thing that is given. Now, the process is similar to what we did with one sample, and we need specific formulas. P bar is X sub 1 plus X sub 2 over N sub 1 plus N sub 2. Okay, we pull the two proportions. And the formula for test statistics Z is P1 hat minus P2 hat over the square root of P bar Q bar over N1 plus P bar Q bar over N2. That's how we get started. And now we need to calculate, according to the given, P1 hat, P2 hat, Q1 hat, Q2 hat. So as you recall, P hat is X over N. So P1 hat is X sub 1 over N sub 1, 56 over 8, 843. And you carry out many decimals or exact fraction. We do the same thing for the second one. P2 hat is X sub 2 over N sub 2. And here's the decimal representation of that. And now we calculate the P bar, X sub 1 plus X sub 2 over N sub 1 plus N sub 2. So that means add 56 and 27 over 843 and 703. And that is P bar. And obviously Q bar works just like any Q, is 1 minus P bar. So Q bar is 1 minus P bar. All right, now we are ready to go through the process. So number one, H0. Now we are dealing with two groups, P1 minus P2 equal to 0, or you can say P1 equals P2, either way. Then the second part is the inequality. We're going to write the same thing with less than, greater than, or not equal. Which one we're going to read? Is there a significant difference between the two proportions? We're not obviously getting the less than or greater than out of it. So P1 minus P2 is not equal to 0, which makes it a two-tailed test. And let's make that a claim. You have to figure out what is the claim. So it's a two-tailed test because it's not equal, and that's a claim. By the way, you want to be consistent. Either use this one, or if you use P1 equals to P2, then H1 becomes P1 is not equal to P2. So either this one or this one. Don't mix them up. So that's the first step. Either one is fine. I'm going to erase my work and I'm going to move on. The second step is to calculate the test statistic. Here's the formula for test statistic. And everything we need, we've done the preliminary calculation. So plug in P1 hat minus P2 hat over the square root of P bar Q bar over N1 plus P bar Q bar over N2. And you come up with the answer. Critical value is 0.01. In the case of a binomial distribution, it's being approximated by normal distribution. One approximation is bad enough. We always use the Z. Alpha is 0.01. It's a two-tailed test. Two-tailed test. Plus minus 2.575. So we draw, and we want to see where this number falls as far as the critical value is concerned. So we notice that Z is either negative or positive 2.575. So those are the tails. And this number 2.4319 is somewhere in between. It's way into the non-rejection region. Because this is way into the non-rejection region, the decision is fail to reject the null hypothesis. So if you're not rejecting H0, in essence, you're rejecting H1, and therefore you're rejecting the claim becomes false. And now we restate what was given. There is not a significant difference between the two proportions. Is there a significant difference? No, that's the case. And we're done with that. As far as the technology is concerned and the p-value, please understand, p-value in this case is the area to the right of test statistic, this area times 2. Why is it times 2? Because it's a two-tailed test. So now, using two proportion z-test and putting the information. So when you put two proportion z-test, it asks for x sub 1, 56, n sub 1, 843, x sub 2, 27, n sub 2, 703. You put that, and then you choose which one not equal, and then you calculate. Notice when you calculate what it gives you. First and foremost, P1 hat, P2 hat, okay, or here, this is P1 hat. This is P2 hat, okay. And this is the value of P bar, 0.5368. If I stop here, 6 changes to 7, as we had it here. Of course, a lot more decimals. Okay, so P1 hat, P2 hat, they show it as P hat. Now, what is this one? So this one, and this one, okay? And what is this one? This is the p-value, 0.015, let's say. Okay, if we stop here, 0.015 or 0.0149, if you stop here, clearly larger than alpha of 0.01, same decision. Fail to reject the null hypothesis. So it's pretty straightforward, everybody. We're going to continue on that thoughts. So now we are looking at the same question, and in part B, construct the 99% confidence interval for the difference between the two proportions. Okay, so similar to what we did with one sample, we are going to use a formula P1 hat minus P2 hat minus E, P1 hat minus P2 hat plus E. So P1 minus P2 is between these two. So what we have is P1 hat, P2 hat, and this is the given information from the previous page. All we have to do, calculate the E. What is the formula for E? Similar to the E that we had, Z alpha over 2 square root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. Again, you have this in your formula sheet. And Z comes from the previous Z that we had. You don't have to look for it. It's the same Z, which was, remember, we had the critical value of plus minus 2.575. So you put 2.575, the rest of them from here. The given helps really. And calculation results in 0.0289. Okay. So pretty straightforward, everyone. So over here, P1 minus P1 hat minus P2 hat, and we're going to subtract this and we're going to add that. So P1 hat minus P2 hat. And by the way, notice I use more decimals here because I want to get closer to the exact value because we had that when put into calculator. And now this number, we are going to subtract and add this number. And so P1 minus P2 happen to be between these two values, negative and positive, negative 0.000878 and positive 0.056922. So because the confidence interval limits, look at the limits, contains zero. Since it goes from negative to positive, it contains zero. There is not a significant difference between the two proportions. Fail to reject the null hypothesis. In other words, the confidence interval results in the same thing if we can understand the interpretation by that, from negative to positive. If it's from negative to negative, that means P1 is less than P2. If it's from positive to positive, that means P1 is larger than P2. That's the idea. Now, at TI calculator, we're going to write confidence interval for two proportion. And again, we put X sub 1, N sub 1, X sub 2, N sub 2, and the confidence level of 99% or 0.99. Notice the number it gives us. Now, this one is very close to what we have. What is this one again? I want to make sure everybody understands the meaning of this. This number means minus 9 times 10 to the power of minus 4. In other words, the decimal that you don't see is here. You move it to the left by 4. Okay? So negative 0.0009. If I want to write this is negative 0.00009. As you can see, it's almost the same as what we have here. So the point being, I want to make sure we understand scientific notation as they reported the scientific notation. Okay. Company A claims that its yogurt cups contain on average a fewer calories than that of a competitor. A sample of 50 such yogurt cups of company A produced an average of 141 calories per cup with a standard deviation of 5.4 calories. A sample of 40 yogurt cups of a rival company B produced on average an average of 144 calories per cup with a standard deviation of 6.3 calories. If the calories of the yogurt cups for company A and B have different variances, use a 0.01 significance level. That is important. We're going to discuss that in a moment. So we are going to write the information for the first group for the second. So I'm going to assume this is the first group. I'm going to assume this is the second group. So N is 50. We're going to call it N sub 1. This one, N sub 2 is 40. Just, to have an idea. This one produces an average of 141 calories for those 50. That is X bar. So X sub 1 bar is 141. X sub 2 bar is 144. Okay, and finally, standard deviation over here for the first group, S sub 1 is 5.4. For the second group, S sub 2 is 6.3, and alpha 0.01. So n x bar s. And there you have it. So first, I want to make sure the given is understood. And of course, alpha is 0.01. All right. Now, the first step, H0 mu1 is equal to mu2. You always start with equality. Now, the next one, H0, what is the relationship here if the carriers of the yogurt A and company B have different, they claim that they have fewer. That means mu1 is less than mu2. That is the claim, and that's a left tail test. Claim, left tail test. Okay, so you could also use mu1 minus mu2 equals 0, in which case becomes mu1 minus mu2 less than 0. Okay, so in other words, just be consistent the way you do the writing. Test statistic has this formula similar to what we had for one sample, x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. You don't have to do much, just look at your table. That's why the given really is helpful. Make sure you take enough time to write that, now plug in. By the way, the 0 that you see here, the formula really contains minus mu1 minus mu2, and this is always coming from H0, which is 0 for us, notice. That's why I didn't even put it in this formula. However, in some instances, you may be testing the hypothesis that there's a precise difference of, for example, 2 or 5 or minus 8. So that's why this may not be necessarily 0. So plug in, do the math, and you get negative 2.3901. Now I'm going to erase my work. And here's what becomes interesting. Critical value comes from the choice of alpha. Alpha is 0.01. Degrees of freedom. When we have technology, it is calculated. When we don't have technology, it is estimated as follows. Smaller of the two degrees of freedom. So this one is 50 minus 1. This one is 40 minus 1. So smaller of n1 minus 1 and n2 minus 1. So we choose, of course, 39. Because 50 minus 1 is 49. 40 minus 1 is 39. That's the smaller of the two. And using the table, this is the left tail test. We get negative 2.426. I'm assuming by now everybody knows how to read the table. So we do the drawing. Alpha is 0.01. Critical value is negative 2.426. And the test statistic is way into the non-rejection region. So when you compare that, this is in a non-rejection region, then the decision is fail to reject H0 or don't reject H0. Now we go back to the very first step to continue with the two parts left. One of them is the claim. If you're not rejecting this one, you're rejecting this one, the claim is rejected and it's false. And you reinstate what was given. There is not enough or sufficient evidence to support the claim that company A's yogurt cups contain on average less calories than that of its competitors. Now, we're going to continue with the p-value and so forth. Okay. But I wanted to make sure everybody understands this piece. Different variances, okay? That's important. When they, even if they don't mention it, you're going to assume that. And therefore, we use this test statistic, okay? That's the idea. All right. We are looking at the same question, part B. Calculate the p-value for the test of previous part and make a decision. Obviously, area to the left of test statistic, this is your p-value. So area to the left of test statistic, and clearly you can see it's larger, you can look it up. And the way you look it up, the degrees of freedom is 39. Again, just to give you an idea how it works, 39, okay. And area in one tail, okay, because we are looking at left tail test. So we look at area in one tail, and we want the numbers. This is, by the way, negative, they are positive, it doesn't matter. We want this number 2.3901, we don't find it. But clearly the positive 2.3901 is here between these two numbers, right? This number, the positive one, is between these two. So the area is between these two, okay, for two-tail test. But it's a one-tail test. So the area is between these two, between 0.01 and 0.025. Now, if it's between 0.01 and 0.025, definitely larger than alpha of 0.01. So degrees of freedom is 39. Test statistic of negative 2.3901 is between these two numbers. Remember, positive or negative concept is understood. P-value is between these two values. Clearly larger than alpha of 0.01. Same decision. Failed to reject the null hypothesis. And the decision is an agreement. Now, let's look at what the calculator gives us. So we go with TI calculator, two sample t-test, and we put the information. Take a look. X1 bar, S1 or SX bar, N1, X2 bar, S2, N2. You put the information, and then we choose less than, and we're going to calculate. This is what it gives us. A couple of numbers we want to look at. Calculated results are different since degrees of freedom has a different value. Take a look. The degrees of freedom is not what we chose. We chose 39 because it calculates it. How does it calculate? Degrees of freedom is a plus b squared over a squared over n minus 1 plus b squared over n2 minus 1. A is s1 squared over n1, b is s2 squared over n2. You don't have to worry about that. It's very involved. But understand, as a result, sometimes we may end up with a result that is different than what the calculator does. Having said that, notice the p-value and the degrees of freedom. Degrees of freedom is different. The p-value is less than alpha, and then you're going to reject H0. So we have a completely different answer in this case. Okay, so it could happen because of the fact that degrees of freedom is different. Having said that, the last part, part C, is asking for 98% confidence interval. So we are going to write everything we had from the previous calculations. And the formula is similar to what we have seen. This one is x1 bar minus x2 bar plus minus e. x1 bar minus x2 bar. I want to remind you, when we calculated the test statistic, the numerator was x1 bar minus x2 bar. So you really have this value. You have to calculate the t, and the formula for E is T alpha over 2 squared of S1 squared over N1 plus S2 squared over N2. So it's important to know this part is this denominator, which is already done, and T was the one that we picked at 2.426. Remember, we put the positive one here because plus minus will take care of that. In other words, this comes from this one. So you have this value, 2.426. That's the T we had before with degrees of freedom of 39. My point being, you really don't have to do much of calculation. Understand this is the numerator here, this is the denominator, and this one is the t value. Okay. Very straightforward. Do the math, minus 3 plus minus 3.04504, and mu1 minus mu2 is between these two. Again, please understand, they may want you to report it this way or this way, which one, whatever they ask you. And negative 6.04504 less than mu1 minus mu2 less than 0.04504. Notice this is negative, this is positive. Because the confidence interval limits contain 0, there is not a significant difference between the two means, fail to reject the null hypothesis. Now, if we do it with the TI, sample 2 interval, we put the information, we definitely get a different answer because the degrees of freedom was different. So minus 5.982 to minus 0.0181. Both of them are negative, does not contain 0. So, and it's important to pay attention to. Calculated results are different since the degrees of freedom has a different value. Because the confidence interval limits are both negative and do not contain 0, there is a significant difference between the two means, reject the null hypothesis. So I hope everybody can see why the difference happens here. If the two are extremely close, then the result from hand calculation and technology calculation will be different. Okay, they're extremely close. If the carriers are, and we are really looking at the same question, if the carriers of the yogurt cups for company A and B have equal variances. So that's the difference. Remember, in the previous one, we said they had different variances. What happens is that everything changes now as far as the calculation of test statistic is concerned. The first step remains the same, and this is the information from the previous one. So H0 mu1 is equal to mu2, mu1 is less than mu2, claim left tail test. I hope you see that step 1 is identical. What happens is step 2, I want to calculate the test statistic, the formula is different. So test statistic x1 bar minus x2 bar over the square root of s sub p squared over n1 plus s sub p squared over n sub 2 is called the pool variance, and sp is squared is n1 minus 1 s1 squared plus n2 minus 1 s2 squared over n1 minus 1 plus n2 minus 1. The formula maybe is a tad complicated, but nevertheless, you have it in your formula sheet. So we're going to calculate this n1 minus 1. That means 50 minus 1, 49 times 5.4 squared plus n2 minus 1, 40 minus 1. Okay, 39 times 6.3 squared and over 4. This is 50 minus 1, 49 and 39. So we get this one. And now we are ready to put that into this and find the test statistic. Again, this 0, remember I said it comes from the from H0, and in some cases may not be the same. And you do the math, you end up with this answer. You're done. Now, critical value comes from the choice of alpha, and the choice of alpha remains unchanged, is 0.01. But here's the interesting part. Degrees of freedom is the sum of the two, which means 50 minus 1 and 40 minus 1. In other words, n1 minus 1 plus n2 minus 1, which is 88. Now, this is the same whether you use the technology or not. However, the difference is as far as the limitation of a table of T-tables normally don't have degrees of freedom of 88. So you have to go to the closest one, which is 90. And it gives us this number, negative 2.368. Now we do the drawing. I highly recommend you do the drawing so you can compare and contrast. So critical value is this number, negative 2.368. 368, and your critical value is negative 2.4316, way into the rejection region. So reject H0. Reject H0 because the value of test statistic is inside the rejection region. Remember, everything we do is about H0, and then we expand. We go to the claim and say, okay, if we are rejecting H0, then loosely put, we are accepting H1, we are accepting the claim becomes true. And then we reinstate. There is sufficient evidence to support the claim that company A's yogurt cups contain, on average, less calories than that of its competitors. So, pretty straightforward. And we're going to continue using the p-value now. So, to use the p-value, instead of the critical value, again, alpha is 0.01, degrees of freedom is given. All of the information that you see is from the previous page. And now we will look for this number, negative 2.4316. And here's area in one tail, here's area in two tails. We want area in one tail. And we look for 88 doesn't exist. We go to the closer one, which is number 90. So degrees of freedom is 90, okay? And test statistic, negative 2.4316, is between these two numbers. Again, please understand it's given as positive, but we are dealing with the negative. The area is the same thing. So between 2.632 and 2.3, this is negative, this is negative. So this number is in between. So area in one tail, because it was a left tail test, it's between these two. Okay, so the p-value is between these two. And clearly less than alpha of 0.01. Same decision, reject H0. Now, what if we do the same thing, but with technology? So we're going to go with two sample t-test. Okay. Now, what I want to mention here, there is a step that is asking for pulled or not. And the answer is yes here. Okay. Because we are assuming equal variances. If not, you say no. Notice when it calculates, the p-value is this, degrees of freedom is 88, and so it's close to ours because we chose 90. We had no choice. And by the way, obviously the p-value is this area to the left of test statistic, okay, which is clearly less than alpha. And in this case is 0.0085 less than alpha of 0.01, same decision. So calculator gives us the same result. Let's look at the last part. We're going to make a 98% confidence interval for the difference between the two means, and we are reminding everybody of alpha, degrees of freedom, t, and the information we have here. So x1 bar minus x2 bar plus minus e. Okay. And so I want to remind everybody that when we did, and e is t alpha over 2 squared of sp squared over n minus 1 plus sp squared over n sub 2, or n sub 1, and then n sub 2. I want to remind you that the denominator for test statistic is the same as this one, and therefore we look at the test statistic and the work that we did. We don't have to do much calculation. This one is already here, and the t is already here, and of course you choose the positive one. So the point being, the amount of calculation, very limited. So these two numbers, this is the answer for E. So now x1 bar minus x2 bar was -3, so plus minus this number. So mu1 minus mu2 is -3 minus this number, which is -5.9216, and plus that number, which is this one. And of course, because the confidence interval limits do not contain zero, notice negative to negative, there's significant difference between the two means, reject the null hypothesis. If we go with technology, we use two sample t-test. We put the information pulled yes, it'll do the job. And look, we have -5.923, very close, to -0.0766, extremely close. And there's really not much of a difference. Extremely close. Again, because the degrees of freedom we had was 88, and what we had to use was 90. Tester claim that weights of male college students have a larger variance than female college students, use a significance level of 0.05 and assume populations or normal with alpha 0.05. So what we want to discuss is F distribution. So F test. For the comparison of two variances or standard deviations, an F test is used. The F test should not be confused with the chi-square test, which compares a single sample variance to a specific population variance. Characteristics. Number one, the values of F cannot be negative because variances are always positive or zero. The distribution is positively skewed. The mean value of F is equal to 1. The F distribution is a family of curves based on the degrees of freedom of the variance of the numerator and degrees of the freedom of the variances of the denominator. So F is S of S1 squared over S2 squared. We choose the larger one because of the limitation of F distribution to be the first group. So S of larger. Okay, so the first group is the one with the larger variance. In most cases, unless otherwise mentioned, the F test has two terms for the degrees of freedom, that of the numerator in 1 minus 1 and that of the denominator in 2 minus 1. And the table looks something like that. You have degrees of freedom. The first one for the numerator is along the top row and the denominator along the left column. This is how we do that. I hope everybody is okay with that. So that's understanding the F test. Now let's go back to the question and let's write the given. Okay. So we are dealing with n being 31, x bar is 168, s is 28. That's for males. N being 29, x bar being 125, s being 25 for this second group females. And so we are going to pick which one is going to be the first group, the one which has a larger S. So it's a normal distribution. Alpha is 0.05, N1 is 31, S1 is 28. I hope everybody can see how we did the calculation. And as we write it for the females, and step one, there are different ways of writing H0. Sigma 1 squared equals sigma 2 squared. Okay. Or sigma 1 squared over sigma 2 squared equals 1. Or sigma 1 equals sigma 2. Which one do you write? really doesn't make much of a difference. What is important when you do your homework or exam, make sure understand how they want. If they write sigma versus sigma squared, numerically the numbers are not the same. The process from here on are the same, but this one you want to be careful. If you write this one, then you're going to write sigma 1 squared is larger than sigma 2 squared, which is a claim, and it's a right tail test because it says large. If you write this one, you write sigma 1 squared over sigma 2 squared is larger than 1. And if you write it this way, sigma 1 is larger than sigma 2. Just be consistent. That's the idea. Use one of them. Which one you decide. And if it's given to you, just be careful as to what's given. Now, the next step is the test statistic. F is S1 squared over S2 squared. Remember, instead of S sub 1, maybe you want to write S sub larger 1 so you don't make a mistake. To choose the larger one as your group, your first group. And of course, in this case, S1 is 28, so 28 squared over 25 squared. So that's a very easy calculation. The next one is critical value from the choice of alpha. Alpha is 0.05, and it's a right tail test. By the way, F distribution, choose it so it's always right tail test. If you make it left tail, two tail test, it is possible to handle it, but stick with right tail test because of the limitation again. Degrees of freedom for the numerator is 31 minus 1 is 30. For the bottom is 29 minus 1 is 28. So F table, there are different tables for F distribution depending on the choice of alpha. So make sure the alpha is the correct alpha. We have it for alpha equals 0.01, 0.05, and so on. So choose it correctly and then move on. So for alpha 0.05, in the top row, look for 30. Left column, look for 20. Because of limitation of room, I didn't have the entire table, but you get the picture, and therefore here's the answer. So critical value is 1.8687. And it is always skewed to the right, and it's always right tail test. And the area to the right of critical value is 0.05. So this is 0.05, okay. And F is 1.8687. So that's the critical value. As far as the test statistics is concerned, it's somewhere here, which is way into the non-rejection region. Therefore, fail to reject H0. Failed to reject the null hypothesis because the value of test statistics falls in the non-rejection region. So if you are not rejecting H0, you're rejecting H1, which is the claim, and the claim becomes false, and you keep on writing. There is not sufficient evidence to support the claim that weights of male college students have a larger variance than female college students. So that's pretty straightforward. Now, let's look at the calculated part, everybody. Two sample F test and plug in the values. Take a look. Two sample F test. S1 is 28, N1 is 31. S2 is 25, N2 is 29. Sigma 1 is not equal to sigma 2. Notice they are looking at sigma 1. Sigma 1 is less than sigma 2. Sigma 1 is larger than sigma 2. In other words, they chose this one, okay? So clearly, you can see the value of F that was calculated as test statistic. You can also see the p-value, which is greater than alpha of 0.05. Same decision. Directional asymmetry, or DA, is a phenomenon whereby in a population, one side of each organism is consistently larger than the other, i.e. left larger than right. An evolutionary biologist studying DA measures the length of the left and right wings of a sample of Drosophila, a type of flies whose members are often called small fruit flies, collected from nature, and she gets this data. So the first one, the length for the left one is 1.34, for the right one is 1.26. The second fly, the left one is 1, the right one is 1.28, and we have a bunch of it. More specifically, how many? We have 17. Part A. The researcher decides to perform a two-sample t-test to determine whether the mean wing differs between the left and right sides of these flies. What type of test will she do? Alpha is 0.05. B, find the 95% confidence interval. Okay, we are going to do the paired t-test, and we're going to discuss that in the next page. What is a paired t-test? Calculate the D, or the differences. So, for example, here 1.34 minus 1.26, put it here, and then imagine you have one sample and do deal with X bar. That's one way to do that. So you create the first one and the next one, 1 minus 1.28, and so forth. Now, all you have to do, deal with this. And because we call this D, the difference, we're going to go with D as follows. D bar, sometimes they use uppercase, sometimes they use lowercase, summation of D over N. I hope you remember that X bar, okay. X bar was summation of X over N. That's the same formula. Or S, if you recall, was X minus X bar, just let's call it S squared, minus X bar quantity squared over N minus 1, right? So if you recall that, now instead of S, just we're going to call it S sub D, and instead of X, we're going to use D. Instead of X bar, we're going to use D bar, and of course, this is S squared, this is taking error. So that's the same thing. So I'm going to erase my word. There's really not much to worry about, and of course, this is the way the TI calculator works. You clear list 1 and 2. You put this one in L1, this one in L2, and then you calculate L1 minus L2 and store it somewhere in L3, because you don't want to do this by hand. And of course, when you put it into a calculator, it gives you the average, D bar, S sub D, and N. So you get that from a calculator, and then you are going to move on with those. Imagine you have one sample. You can use the formula here or formula for just one sample is for the mean. All right. Two means two dependent samples matched pairs. Key concept. Testing hypotheses and constructing confidence intervals involving the mean of the differences of the values from two populations that are dependent in the sense that the data consist of matched pairs. The pairs must be matched according to some relationship, such as before and after measurements from the same subjects. Good experimental design. When designing an experiment or planning an observational study, using dependent samples with matched pairs is generally better than using two independent samples. Hypothesis test. Use the differences from two dependent samples, matched pairs, to test the claim about the mean of the population of all such differences. So it becomes the mean D bar. Confidence interval. Use the differences from two dependent samples, matched pairs, to construct the difference interval estimate of the mean of the population of all such differences. D represents the individual difference between the two values in a single matched pair. Mu sub D mean value of the difference D for the population of all matched pairs of data. D bar, mean value of the difference of D for paired sample data. So this is for population, this is for sample. S sub D is standard deviation of the difference for the paired sample data in number of pairs of sample data. Remember, in reality, almost we never have access to the population. When the values are dependent, do a t-test on the differences. Denote the differences with the symbol D or lowercase d or uppercase d, the mean of the population differences with mu sub D or mu sub D, lowercase d or uppercase d, and the sample standard deviation of S sub D or S sub D, lower or uppercase. So that's pretty straightforward, everybody. Degrees of freedom is n minus 1. Use either D or D. D bar summation of D over n or summation of all these formulas that you see. If you look at the X bar and you change the D to X, they are identical to those formulas that we have seen. All right, we're going to continue now working on that. And so with that explanation, we are ready to do so. H0 mu sub D equals 0, and H1 mu sub D is not equal to 0. That is the claim, and it's a two-tailed test because the question is there a difference between the two sides, left and right, okay? So whether they differ or not. So I hope you see T was X bar minus mu over S over square root of N. Now we're going to use D bar, and it's been already calculated. Just plug in. So that's why this is helpful. Plug in. And again, this comes from H0, and it's always 0 for us, but it may not be. Critical value, alpha is 0.05, degrees of freedom in minus 1, 17 minus 1, results in the following. We go to the table. Okay, so this is alpha over 2, and the critical values are negative and positive 2.120. Where is this number? Somewhere here in between. Way into the non-rejection region. Fail to reject H0 or do not reject H0. So if we are not rejecting H0, we are rejecting H1. The claim is false. There is not sufficient evidence to support the claim that the mean being differs between the left and right sides of these flies. She cannot conclude that this population possesses DA because the mean length of the wings on the left and right sides do not differ significantly. All right, so as far as technology is concerned, for TI calculator, you can use matched t-test. So test it in the following manner. Data enter mu 0 equals 0, and the list L sub 3 contains L sub 1 minus L sub 2. Choose right tail test, left tail test, or two tail test. Of course, in this case, two tail test. Do the calculation, it will give you the answer. All right. The second part, B, find the 95% confidence interval for the difference between the means. Again, reminding you of what we had there, and it's, as you recall, it was X bar plus minus E. Now it's D bar plus minus E. Okay. This is a 95% confidence interval. Critical value is plus minus 2.120, as you recall. And D bar plus minus E. E is T alpha over 2 S over square root of N. So just this one is 2.120. S is 0.2283 over square root of N is 70. So you are going to write D bar, which is negative 0.0906 plus minus this number. So this is one way to report it, or subtract from it, add from it, and say mu of these between the two. So either you report it this way or this way. Which way? The way they ask you. Since 0 is contained in the interval, the decision is to not reject the null hypothesis H0 mu sub d equals 0. And that's exactly what we had in our decision making part A. You can put matched pair T interval on L1 minus L2 and do the math. All right, and ecologist is concerned with whether pollution entering part of a preserved area is compromising the health and growth of an endangered species of snake. To determine this, he decides to measure the length of a set of mature adults from the polluted area and an unpolluted area. The researcher decides to perform a two-sample t-test to determine whether the mean length of the snake differs between these two areas with alpha of 0.05. So, unpolluted in centimeters. The first one, the length is 27 centimeters, and it goes down to the second, third, and picks up 15 and checks them out. For the second group, the first one is 25. This is a polluted area and chooses 17. They don't have to be this. And so we need to calculate the following. And we're going to assume different variances. As you recall, when we did the part about the yogurt, we had the equal variances and assume different variances. In this case, they don't tell you. Always assume different variances unless otherwise mentioned. So for each group, we have to calculate the sample standard deviation, mean, and size. Obviously, the size for this one is 15. For this group is 17. You calculate the mean, that means add them up, divide by size. You use standard deviation formula to calculate that, and you do that for both groups. So that's what we need to begin with, everybody. Now, T is x1 bar minus x2 bar over square root of s1 squared over n1 plus s2 squared over n2. H0 mu1 equals mu2, and what is H1? They are not equal. Mu1 is not equal to mu2. That is the claim, and that's a two-tailed test. Next, we got to do test statistic using this formula. That's why this comes handy. Put it in, calculate it. You get 2.8022. Critical value comes from the choice of alpha 0.05. Again, we want to go with the, again, without the calculator, degrees of freedom would be smaller of the two. One of them is 15 minus 1. One of them is 17 minus 1. So we're going to go with 15 minus 1 or 14. And from the table, we get plus minus 2.145 because it's a two-tailed test. Now, to understand this, we're going to do the drawing. So the critical values are negative and positive 2.145. Test statistic is 2.8022, way larger than 2.145 when way into the rejection region. Because of the location of that, reject H0. So if you're rejecting H0, you're accepting H1, the claim becomes true, and you're right. There is enough evidence to support the claim that the mean length of this snake differs in these areas. It is larger in the unpolluted area since test statistic is positive. In fact, gives you an idea Okay. If it were negative, it would be less. Now, for two sample test statistic, mu1 is not equal to mu2. We get the following. I'm going to assume everybody has put in the information. By now, we know what to do. Calculator uses a different degrees of freedom. It calculates this way. Take a look. If we go through this process, I mentioned that this is how the degrees of freedom is calculated, which is pretty involved, 29.38. And if you were to go with that, you can go with the rounding to 29. So notice the p-value here. The p-value would be the area to the right of test statistic, everybody. This area. Okay, to the right of test statistic. Step 3, critical value alpha is 0.05, degrees of freedom is 29, round down always. Okay, plus minus 2.045. And the p-value is 0.009. Take a look here. 0.00. If you stop here, you change the 8 to 9 because next to it is 9, which is less than alpha of 0.05 and reject H0. Although the calculated result is different as far as the degrees of freedom is concerned, okay, but this one is the same, and the result, whether we use a table or a calculator, is the same.